this last example, we are going to be working through a special case of where we very much like to use our complement rule of probabilities. But first, we need to set up our experiment here. Our experiment is going to be having a random PIN number from a 4-digit PIN number. So this is essentially what the type of PIN number that banks use for debit cards and things like that. And our PIN numbers are going to be 4 digits randomly chosen from 0 through 9. And the first thing that we need to figure out is our sample space, our number of ways that we could essentially write a PIN number. To do this, we're going to need our fundamental counting principle from section 7.1. And I'm first going to calculate our number of pins that we can make if the digits can be repeated. Just a little bit over here, I'm going to list out all of our options for the digits, which is 0 through 9. And now, to figure out how many pins can be created when the digits can be repeated, well, we have a 4-digit PIN number. So I'm going to look at each of the digits individually for digit 1, digit 2, digit 3, and digit 4 of this PIN number. The first digit, how many options do we have to choose from? Well, we're choosing from 0 through 9, and we can see that there's 10 different numbers there to pick from. And now we're saying that the digits can be repeated, so we have the same for 2, 3, and 4. They're all 10 options. And now our counting principle says we just multiply these together. So 10 times 10 times 10 times 10 gives us 10,000 different PIN numbers that we could write for a 4-digit PIN number. The next one, I want to figure out how many pins can be made if the digits cannot be repeated. So once again, we're going to have our 4 digits of our PIN number, but now we're saying they can't be repeated. So our first digit, we can choose any of the 10 options. But now we have essentially picked one of those 10 options. One of them has been used up. So the second digit cannot be whatever one was chosen. So we're now down to 9. And now out of those 9, one of them was used for that second digit. So the third one only has 8. And now one of those 8 was used for that third digit. So the fourth one only has 7. And now we can multiply those together to get our number of pins when the digits cannot be repeated to give us 5,040. So now, the probability that we want to find here is, first, we have that our PIN is selected by 4 digits at random, and the digits can be repeated. What is the probability that the PIN contains at least 1 8? This is very hard to calculate if we just try to think of this as being at least 1 8. Because the at least part there tells us that it could have 1 8 in the PIN number, it could have 2 8s, it could have 3, or it could be all 4 8s in our PIN number. It could also, if it had 1 8 in it, that 8 could be in the first position, the second, the third, the fourth position of the PIN number, and we would have to figure out all of these different ways that we could write a PIN number with at least 1 8 in it, and that's a lot of work. That would be a lot of steps to try and figure out how many different pins we could write like that. What makes this a lot easier is to think about our complement rule. Because if our PIN number has at least 1 8 in it, the opposite of that is it has no 8s. Because you're either greater than or equal to 1 for the number of 8s in the PIN number, or there's none, there's 0 of them. So we are going to figure out the number of pins with no 8s. And we can do this by thinking about the 4 digits individually and using our counting principle. So we are in the situation where our digits can be repeated, but now we want how many don't have an 8 in it. So if I'm looking at my numbers up above in the top right, I'm going to cross off the 8 because that 8 is not an option. How many numbers do I have left to choose from for that first digit? Well, we have 9 options there, so my first digit has 9 options. And now we said they can be repeated, so the second, third, and fourth also have 9 options, and we can just multiply this together. So now this gives us 9 times 9 times 9 times 9, which is 6,561 different pin numbers that do not contain an 8. And now we can use this to find our probability of having no 8s. Because our probability of no 8s is going to be our number of pins with no 8s out of all of the pins in total. So we have 6,561 pins with no 8s in them out of our 10,000 different pins when they can be repeated. And that then gives us 0.6561 for that probability. And now lastly from this, we can use our complement rule to find our probability of having at least 1 8. Because that's simply just going to be 1 minus our probability of no 8s, which is going to give us 1 minus 0.6561, which is 0.3439. And that would then be our probability that the pin number has at least 1 8 in it. The next one, we want to do this same thing, but now the digits cannot be repeated. And now from there, what is the probability that it has at least 1 8? Well, we're going to first, once again, look at our complement. So find the number of pins with no 8s in them. It's still a 4-digit pin number, so I'm going to have 4 blanks to fill in. And our first digit of the pin number, we're looking at 0 through 9, but we're taking away that 8, so it only has 9 options. And now our digits cannot be repeated, so we're going to go down by 1 for each of these blanks. So 8, 7, and 6. And now we can multiply those together to give us 3,024 pin numbers that do not contain an 8, and there is also no repetition with these. So next, our probability of no 8s when we have no repetition. Well, we have 3,024 pins with no 8s out of the 5,040 pins when there is no repetition. So that then gives us 0.6 as that probability. So now lastly, our probability of at least 1 8 when we have no repetition is equal to 1 minus our probability of no 8, which we got as being 0.6, which then gives us 0.4 to be able to answer this question, that when there's no repetition, the probability of having at least 1 8 is equal to 0.4.